In this session, we'll be learning how exactly we can write an ARM code in order to sort the given data in ascending order. Here we are using bubble sort algorithm to arrange all this data in ascending order. Bubble sort works by repeatedly swapping adjacent elements if they are in the wrong order. This process is repeated n-1 times for n elements until no swaps are needed. Okay, so we have here 32-bit data shown here. Okay, almost 6 values are there and it's in random order. We want it to be sorted in ascending order. If you see here, we have a label C value wherein all this data is stored. Okay, and what we want is we want to copy it into this particular address pointed by the label D value, okay, in a sorted order. Here area is nothing but assembler directive which instructs that some segment should be given in the memory so that we can store the final result. Okay, and data1 is a random name, data, because this section will store data values, not instructions, and read write because we want to be able to modify this particular content. Okay, and the C value here is in the read only region as specified here, because we don't want any modification to be carried out in any content till here. Then what we have is nothing but its code here to indicate these are nothing but instructions. Ascending is a random name. Area here indicates that some storage area should be created in the memory in order to store this particular content. Okay, entry here indicates where exactly code starts. Start is a label. Okay, the very first instruction which we see here is move R8, #6 because we have 6 values here. Okay, LDR R2, equal to C value, LDR R3, equal to D value. What happens here is this address of this particular label is stored in R2, address of this label is stored in R3. Actually, in this particular code, what we want to do is first this entire content we want to copy into our read write section. After copying that, we will start with the sorting work. Okay, let's see how exactly this code works. The very first line stores the value of R8 as 6, okay, which is the total number of contents to be altered. R2 has the address of C value, which is 6C. Okay, as you can see, the data which is given here, all 32-bit values are occupying 4 locations each and is stored as given in this particular code. Okay, now we want to check the next value, which is nothing but the address of D value, which is stored in R3, which is, okay, initial value you can see is all zeros. Okay, we want this value to be copied here and then we want to swap the positions. Now let's see how that is done. And whenever you want to open a memory window, you have to just go to view and we have to click on memory window. You will get all these options. You can choose any one. Okay, so let me just check what is happening here. Okay, first we have a loop here, and what this statement will do is whichever location is pointed by R2, so initially this will be the location pointed by R2, so that is 6C, that content is copied into R1. Okay, and then R2 is incremented by 4. What that should do, we'll see that. If you see here, the very first value is now present in R1. Okay, and R2 value is incremented by 4, so 6C plus 4 is nothing but 70. Okay, so what should happen? As already told, you want to copy this content to this particular memory location. If you see the next step, okay, store R1, content of R3, #4. So what is happening is the content of R1 is nothing but 4. Okay, 4444. So this value is now stored into R3. So as shown here, R3 initial location was 0x4 0 0 0 0 0 0 0. Okay, now what we want to do is we want to increment the address of R3 so that initially it was pointing at this location. We want to store the next data, so its initial value is added plus 4, so it should now point at this particular location. Let's see what is happening here. 4 0 0, all this 4, last you can see 4, right? That is the result of incremented address. Okay, what is the next step we want to do? Similarly, we want to copy all 6 items. So one item is already copied out of the 6. We are subtracting by 1 and comparing if R8 is 0. Let's see how that happens. But in our case, R8 is not 0, so it will branch back to loop 0. Okay, now if you see here, next data is copied in the similar way. Okay, and I'll just place it in the location of D value, okay, where we want all data to be copied to. Let's see how that works. Okay, in this way all 6 datas are now copied. Okay, so this loop's work is done. The only task done by loop 0 is to copy the content of C value to D value. Okay, any sorting, nothing is done till here. Okay, now let us see what exactly is being carried out here and why exactly are we copying here. This is read-only content, we can't modify anything here. So at first only we are copying and pasting it here so that we can do any manipulation with values. Okay, let's see here. Here R5 is a counter, we are taking it as 5 because total number of elements minus 1. Okay, R7 is a flag which is used to indicate whether swapping happened or didn't happen. Next, R1 points at D value. Let's see what exactly that is. D value is the initial location, so it will be pointing at the very first data. Now what they are doing here is nothing but content of R1 is moved to R2. Okay, and R1 is incremented by 4. What is the content of R1? That should be 4 4 4 4. This term should be copied to R2. Let's see if that happens. Yes, so the very first value is now copied, and what we want to do is we want to load next content. See, first value we have copied to R2 and R1 is now incremented because R1 was initially pointing at the first address. Incremented by 4 means it will be pointing at this location, so that content is copied to R3. So what will happen now? R2 and R3 will have these 2 values, and as expected comparison is carried out between R2 and R3. Okay, as soon as comparison is done, internally subtraction will happen based on if R2 is less than R3 or R2 is greater than R3. The conditional flags here are modified. Okay, fine. So based on this, what will happen is if R2 is equal or less than R3, it will jump to loop 2. That is this particular location where R5 is subtracted by 1 to indicate one comparison is done. What we should know is nothing but the first value, it is compared with second value. Because it is ascending order, lowest value should lie in the first position. If each value is lower than the second value, any changes are not required, so we are reducing the comparison. But in our case it is 4 4 4 4 and here it is 1 1, so obviously first value is greater than the second value. In that particular case swapping should happen. So this you have to focus here, how exactly they are doing the swapping. Now in our previous step already R1 will be pointing at the second location. If swapping is to be carried out, okay, we already know R2 has the first value, correct, 4 4 4 4, and because of this particular instruction here, okay, as we can see already R1 was pointing at the second memory location. So the first value is now stored in second memory location. After storing the 4444 value in the second memory location, we are subtracting the R1 content by 4 so that it can point into the first memory location. Let's see how that happens. Okay, if you see here, the first value which was there in R2 is directly stored in the second memory location, and then we are reducing the address of R1 so that now it points at this location, because in this location we want to store the content of R3. So that is carried out in the next step. Okay, so this is one swapping that we did. Fine. And then what we should remember is, because the address is now pointing at this particular location, we need to move it forward, because of which we are adding R1 with 4, so that now it again points at the second location only. Along with that, we have set R7 as 1 to indicate swapping is carried out. Okay, and next it comes here to indicate that anyhow one particular comparison is done, and then we are comparing R5 to 0, which is not true, so the loop continues. Okay, let's see what happens next. In the next case, we will take R1 content, which is nothing but the second value. We will store it in R2, and then we will increment R1 plus 4 so that it points at next location. Let's see how it happens. Okay, so now R2 is nothing but 4444. Okay, and we take the next value in the register R3 as shown here. Okay, so now what should happen? These should be compared. Will swapping happen here? Yes, it will happen, because this is greater than this. Okay, if it was less, then directly one comparison was reduced, but it is greater, so it continues. Okay, so here it should carry out these tasks. Let's see how it will happen. Okay, R2 content, which is nothing but 4444, is now copied into R1, which is nothing but memory location pointed here. Okay, and after that, this particular address is decremented by 4 so that it will point at the previous location. Okay, and R3 content is stored in that particular location. Again, R7 is set as 1, and address here is incremented by 4 because we want to point at the very last location of the comparison. Okay, let's see what happens next. Again, our 4444 is loaded into R2, and 2222 is compared. After comparison, okay, because R2 is again greater than R3, swapping is required. Next value is taken, but in this particular case you can see 4 is actually less than A. So what will happen in this particular case is, it will jump here and reduce one particular comparison. Then this value is compared with the next value. Okay, and as we already know, swapping happens. Okay, if you notice here, okay, this particular loop is broken now. If you notice one thing, okay, if at least in one position swapping has happened, R7 will be set as 1. Okay, so in that particular case, you branch back to initial case. Okay, and all comparisons are carried out. Okay, but if there is no swapping at all, it means that the current whatever arrangement is there, it is proper, so no need of branching back. Fine. And next what happens is nothing but we are branching back to next term. This continues until R7 value is set as 0, which means that particular iteration has already arrange the data in the desired order. Now I have made a slight modification, that I have changed LS to LT. BLT, branch if less than,
used for signed comparison.
If in case the given list of values we assume it is signed numbers, if it is signed means any number which has MSP as 1, it is considered as negative numbers. Okay, and one thing you should know that the most negative number present here is nothing but 8. In case of positive numbers there will be no confusion. Okay, let's see what output we get in this particular case. See, it's ascending, so 8 comes first, a then 1 2 3 4. So this is how it has arranged in ascending order for signed numbers. Okay, let's see what happens if this code is meant for descending. Let me just make minor modification here. It is nothing but
BHI is branch if higher, used for unsigned comparison.
we have a at first, then 8 4 3 2 1. Okay, but this is if it is unsigned descending, but if it is signed descending, then we had to change this to BGT.
BGT, branch if greater than, used after signed comparison.
Okay, if you see here 4 is the highest number, 3 2 1, and then a and 8 are treated as negative numbers.